Aloha and welcome. In this video, we're going to be talking about linear and binary searches. We've talked about them before. We're just going to compare them right now and show them side by side. So we'll go ahead, open up the book to this chapter. So linear search, as you remember, it's a search where we're looking through each element of the array. It doesn't have to be ordered necessarily, but you look through each element to find a key that you're looking for. If it's not in there, you're going to go through every single one. If it's the first key, you're only going to do one comparison. But the idea of this is that it's really dependent upon where it is in the array that you find it that determines the amount of time it takes. So it's relatively inefficient. For a small array of like 3 to 5 elements, that's not hard. It's just going to be 3 to 5 comparisons, no big deal. But if you have a million items in there, that's going to take up to a million possible searches. If it's not in there, then you just search a million for nothing, and it's very costly. So that's implemented in Java as following. So you have your linear search, you take in the array of numbers and the key that you're looking for. You do a loop over the entirety of that array. So you're going to loop from the 0th element to the length, not including that last one. And then you're going to say, hey, is the item here equal to my key? If it is, you return it. If not, you keep on looping through it. And then eventually, if you loop through everything, find nothing, you return -1, letting them know that it wasn't there. And then in the body of the code here, it's just going to have you ask for an integer and then compare, do a linear search for that. And if you can't find it, if it returned -1, you just say it wasn't found. Otherwise, you tell them what the index was for that. So you look at this linear search algorithm, how many comparisons are performed by linear search, for example? So if your key is 94 in here, you know that you're going to have to go through 1, 2, 3, 4, 5 comparisons. So you put in 5, you can do the rest on your own and note that this one isn't in there. So how many is that? So binary search, we just talked about that in a previous video. Binary search is going to take your entire array. It has the caveat that that array, well, first of all, it has to be directly accessible. So you can do a comparison in just one microsecond if you're doing microseconds. But the second aspect of it is your information in there has to be ordered. So it has to be ordered and it has to be directly accessible. If those two things are met, then we can do a binary search on it. And a binary search is going to take the entirety of your array. It's going to look at the middle element. And if the middle element is greater than the value that you're looking for, then you know that you're going to be looking in the first half. If it's less than that, then you're going to be looking at the second half. So what happens is the bounds, the low and the high end of what you're searching in that array changes depending on what that middle value is compared to the thing you're searching for. So we will go ahead and look at the code for that. So in the code here, we have binary search. It's taking the array and the thing we're looking for. It sets a low and it sets a high, and that's just the boundaries of the array the first time you go through here. And it says, loop until the low passes the high. And while we're doing that, we're going to take the midpoint. So it's going to be taking the midpoint, which is going to be the ceiling of the high plus low divided by 2. So if you have like 7 elements, that's going to give you 3.5, which rounds up to 4. So it'll be the 4th element. So you're going to cut the range to either the left or the right. So when we look at that middle element is less than the key that we're looking for, then we know that it's going to be in the high end of the high end that we haven't searched yet. So our new low is going to be mid, what we just looked at, +1. So it'll be we're getting the half of the thing that we haven't checked yet. Because each time we go through this, we're reducing our search size by half. So then after we've done that, we've set that, we go up there and again, we take the midpoint of it. We look at the midpoint and we do a comparison and we do the same thing. If it's less than, then we're going to take the upper range of things else. We're going to change that. We're going to take the lower half, which is still the previous low, with the high being that middle point -1. So it's a little bit confusing, but just go through that in your mind, pick an example, make it 3 or 4 elements, and then walk through this code and see how that works for you. But it's simply, we're going in taking the middle point, comparing, the two, and we're going to either the lower side or the higher side. And that calculation there with low equals mid plus one or high equals mid minus one is what does that. That's what changes the boundaries of our array that we're searching. So it's the same way. It asks you for an integer to look for, and then it does the search for you there. So now we get into questions here. Can the array blah, blah, blah be used as input to binary search method? Well, the one requirement that we have is that they be in order. Are these in order? That should be what you're looking for. Also with the binary search items, how many items are compared to the key by binary search for each example? So let me take the first one. We're looking for 74. 74 is over here. So the way this works is we take all the elements. We have 1, 2, 3, 4, 5, 6, 7. So we take 3.5, round it up to the fourth element. So it's going to be starting right here. This is our midpoint. So is 34 greater than or less than? Well, 34 is less than 74. So we're going to go ahead and take the next half of it. So we're going to look at 41 through 68. We take the middle element, and that is 74. So we got there in 2 searches. So I'll go ahead and let you figure out the next one, and the next one is not in there, so you'll need to go through the whole thing to figure out how many you've got. Or you can just use your logarithm calculation that we had from last time to figure that out. So linear and binary search algorithms. Both linear and binary search algorithms appear in the IDE below. The methods are modified to count the total number of comparisons for each algorithm. So it's going to show you the comparison of how they both perform here. So if we had an element 45, and if we're looking at our list here, okay, so here's the list that they have us set up with. So if we're looking for the 45th element in there, or the element 45 in this list, it's not the 45th element, obviously. If we look at that, it's going to tell us that using linear search, it takes 7 comparisons, and binary is 3. So that looks like, binary wins out. So in general, we know that particularly on large sets that we have, or large lists, or whatever you want to refer to this as, on large N here, we can do much better using binary search. But are there cases where linear search is better? And we can find that out by trying each element. And the first element should give you an idea, because in linear, the first element, you're going to get there in 1 try. So we put in 2 there. You'll notice that linear is only 1 comparison, whereas binary is 3. So, hey, linear wins 1. But we take the second element in there and we run it. And all of a sudden, you notice that we're running neck and neck. It's 2 and 2. Take the third element in there, which is 7, run it. And you see that there's still neck and neck. Take 10, and where are we at? So with 10, you'll see that we've got linear is 4 and binary is 1. So we're getting more efficient on the binary side. Now, what if we take 11? 11? Then linear is 5 and binary is 3. So in most cases here, we've got binary beating linear, but it's only on the edge cases that we find that it's better for linear. So when we've got just one, thing there, we could even, if we had less, if we actually modified this and had less elements, you would find that linear would lose its winning streak, because I think if we just had 2 elements alone in here, if we just had 2 elements in there and we were looking for the first element, you might find that we're equal. Yeah, we're equal. So if we, because in a situation like this, with a smaller array, you're going to, the binary search is going to be just as fast as the other. But if it wasn't, and we had a longer array, in that case, linear would, find it faster because it's the first element. You don't have to go down. But again, even if you're talking about looking for the element 2 in here, and you're talking about needing, what was it, three, I think, three comparisons. If that's a microsecond per comparison, 3 microseconds is nothing. It's almost, it's imperceptible. So that's not a big deal. But you'll see that as we add elements in here, it gets to be, and I won't add the elements here. You can do that. You'll have a chance to do that in a project coming up in one of your assignments. But as you get larger and larger sets here, binary is much more efficient than linear. So anyhow, that's been our exploration of linear versus binary search algorithms. If you have any questions about this, feel free to ask me. Send me an email. We'll set up a Zoom meeting if you need. I'd be happy to help you. But otherwise, I'll see you in the next video. Aloha.